So let us go forward. So let us look at the equation of motion for of the sprung mass first. So if we just apply Newton's second law, what are we going to get? We are going to get ms times zs double dot t, which is nothing but the acceleration of the sprung mass, that is going to be equal to minus ks times zst minus zut. I am just writing from the free body diagram, and then we will have minus bs times zs dot t minus zu dot t, right, plus FAT. So rearranging this equation, we are going to get ms times zs double dot plus bs times zs dot plus ks times zst, that is going to be equal to bs times zu dot t plus ks times zut plus FAT. Alright. So, this is the equation of motion for the sprung mass. So, let us call this as equation 1. So, similarly we can write the equation of motion for the unsprung mass. So, what would we get? Once again we need to equate all the forces on the unsprung mass, right. So, we will get mu times zu double dot t, that is the acceleration, that is going to be equal to ks times zst minus zut plus bs times zs dot t minus zu dot t, right, minus kt times zut minus zrt minus FAT, right. So, that is the equation of motion of the unsprung mass. So, if we rearrange, what will we get? We get mu times zu double dot t plus bs times zu dot t plus ks plus kt zut, that is going to be equal to bs times zs dot t plus ks times zst plus kt times zrt minus FAT. Okay. So, this is the equation of motion for the unsprung mass, right. Okay. So, now these two equations can be rewritten in this form. So, equations 1 and 2 can be rewritten as, see we are trying to analyze the vibrations, right. So, to the road inputs, okay. So, that is what we are trying to do. So, in order to facilitate that, what we do is that like we are going to group these two equations and write it in a form which will enable us to do the corresponding analysis, right. So, we are going to we will fill up these elements shortly, but first let me write the structure so that it will become clear as to what we are after. So, let us look at these terms first, okay. So, what are we looking at? So, let us say like we call this as our vector z of t, which indicates the state of the system, right. So, because it is a 2 degree of freedom model, so the vector z, I am denoting a vector by putting a tilde underneath it, right, and a lower case character. So, the vector z of t is a column vector that consists of the 2 degrees of freedom which are essentially zs and zu, that is the displacement vector. So, zs dot zu dot will be the derivative of the displacement vector, let me denote it by z dot, right, which will correspond to the velocity, and this will be the second derivative of the displacement vector, which will be the acceleration term, okay. Suppose if we look at 1 and 2 and fill it, what will be these terms? We will get ms 0 0 mu, let me fill it up, and then we will have bs minus bs minus bs and bs, and then like we will have ks minus ks minus ks and ks plus kt, right, and this is going to be equal to something times zr t plus something times fat. So, these are the two inputs, right, which are coming in. So, zr essentially we will have 0 and kt, right, from this equation. Here we will have 1 and minus 1. Okay. So, this is the general structure of this equation. So, this 2 by 2 matrix is what is called as the mass matrix M. Okay. So, matrix we will indicate with an uppercase character with a tilde underneath it. Okay. So, that is our mass matrix. So, this let us call it as the damping matrix C, and this is what is called as a stiffness matrix K, and let us call these two vectors as some B1 and B2, okay, which are multiplying ZR and FA. Okay. So, this implies that thus the governing equations can be expressed as the governing equations of the quarter car model, right, can be expressed in this generic form this. So, this will be mass matrix multiplying the acceleration vector plus the damping matrix multiplying the velocity vector plus the stiffness matrix multiplying the displacement, that is going to be equal to some vector B1 multiplying ZR plus the vector B2 multiplying FAT. Okay. So, that is the governing equation, alright. Okay. Now, we are going to ask ourselves a question, right. So, in vibration studies, like many times we are interested in figuring out what are the natural frequencies of the system, so that we can identify the modes of vibration of the particular system. So, even for the suspension system to analyze ride quality, like we are interested in what are the natural frequencies of the sprung mass and the unsprung mass components, right. So, let us ask ourselves the question, right, how can one determine the natural frequencies of the system. So, if we consider this in general, this is a multi degree of freedom system, right, in general. In this case it is a 2 degree of freedom system, but this will be the general structure for the governing equation of a linear multi degree of freedom system model. Okay. So, we can see that it is a linear ODE, but then like it is a vector matrix ODE, right. So, that is what we have got. Now, if we want to find the natural frequencies of this system, we have to figure out a generic way to do it. If we look at a simple 1 degree of freedom spring mass damper system, let us say consider a 1 degree of freedom mass spring damper system, right. So, that all of us are familiar with, right, whose governing equation is given by, let us say, some mx double dot t plus cx dot t plus kxt equals some f of t, right. So, x being the 1 degree of freedom, that is some displacement, right. So, now what is the natural frequency of the system? its natural frequency omega n, as all of us know, is going to be square root of k by m, right. So, that is the answer for a 1 degree of freedom system. So, now the question becomes, how do we do it for this system, this multi degree of freedom system. So, this I am going to leave it to you as an exercise. The natural frequencies of the multi degree of freedom system can be obtained by solving the following equation: determinant of minus omega square times the mass matrix plus the stiffness matrix equals 0. Okay, so, this I leave it as a homework to figure out how. Okay, so, this is standard result from vibrations. Alright. So, if this were the case for our quarter car model, what will happen? By the way, what is the definition of natural frequency? It is a frequency at which the undamped unforced system will oscillate when we subject it to a perturbation. Okay, that is the definition one needs to use to get this formula. Okay, so, please use the definition, apply the definition to this general governing equation of a multi degree of freedom system, and you will get this result. Okay, so, please do it as an exercise. So, for the quarter car model, we immediately have this equation to be or the elements of this equation as follows. The mass matrix is this, the stiffness matrix is a 2 by 2 matrix whose elements are these. So, we have already identified them, right, when we derive the equations of motion. So, now if we put them together, we essentially get the following. So, we will have determinant of minus m s omega squared plus ks, then we will have minus ks, then minus mu omega squared plus ks plus kt, this is equal to 0. Okay. Then if we simplify this, we will get ms mu omega power 4. I request you to fill up the intermediate steps. Okay, this is simple algebra. So, I am just writing down the final polynomial that we will obtain. Please double check this result. So, minus ms times ks plus kt plus mu ks omega squared plus ks kt equals 0. So, this, if you simplify this is what you get. Okay, pretty straightforward. Okay. So, now we can observe that this is what to say a polynomial. On the left hand side we have a polynomial in omega of order 4, but then we can observe that we only have the what to say even powers, right. So, we can think of it as a quadratic polynomial in omega square. So, if you substitute omega hat to be omega squared, you will get a second order polynomial in omega hat. So, one can solve it very easily. So, if you please do that, okay, solve the solution can be obtained as, okay, once again please do this exercise. You know, I am just writing the final result. Omega squared is going to be ks plus kt divided by 2 mu plus ks by 2 ms plus or minus we will have ks plus kt whole square ms square plus ks squared mu square minus 2 times kt minus ks ms mu. Okay, the whole thing divided by 2 ms mu. Okay, so that's the equation. So, you can see that it is certainly not square root of k by m, that what we expect for a that what we got for a single degree of freedom system. Please note that this is only omega squared, then we will have 2 choices for omega squared, then take the positive square root for the 2 choices, you will get the 2 natural frequencies. So we can see that, you know, like if we want to just extrapolate from the result of the single degree of freedom system, we are not getting something similar, right. Our first intuition would be to do that extrapolation, but the result is something else. However, right, when the tire stiffness Kt, please do the above exercise, that is going from here to here, I leave it to you as homework. Okay. Once again, a pretty straightforward algebra. Okay. So, when the tire stiffness Kt is much higher than the suspension stiffness, Ks, okay. One simplification that we can do is that, like, we can take Ks plus Kt as almost Kt, right, and then we can consider Kt minus Ks as almost Kt. Okay. Using this simplification, what we will get is that if you do the algebra, you will observe that this omega natural frequency, the first and the second natural frequency will reduce to square root of Ks by Ms and square root of Kt by Mv. Okay, but this is true only if the tire stiffness is much higher than the suspension stiffness. This also can be shown very easily. That is, in the above equation, you just wherever you have Ks plus Kt, you replace as Kt, wherever you have Kt minus Ks, you replace as Kt once again, right. So, then we get a simplified equation that can be used to get a first cut idea about the 2 natural frequencies. Okay. Now, we can see that this is more or less analogous to, or looks to be in the same pattern as what we had for a single degree of freedom system. So, in other words, when the tire stiffness is much more than the suspension stiffness, the response of the 2 masses, right, can be analyzed in a decoupled manner. Okay. So, that is the implication. So, this is what is called as the natural frequency that corresponds to the what is called as a sprung mass mode. Okay. And this is the natural frequency corresponding to the unsprung mass. Okay. So, one can immediately observe that the value of Kt by Mu is going to be much higher than value of Ks by Ms. The tire stiffness is going to be more and the unsprung mass is going to be lower than Ms, right, by and large. So, we can immediately observe that the value of this omega n unsprung mass is going to be much higher than the natural frequency corresponding to the sprung mass mode. Okay. So, this is a simple analysis that one can do for getting an idea about the natural frequencies of this suspension system, right. Okay. So, there are some standards, you know, like which are also used to evaluate the corresponding metrics, you know, associated with the vibration levels, since we are discussing ride comfort, right. So, let us identify these standards. So, there is a standard ISO 2631, okay, that prescribes methods to quantify whole body vibrations, whole human body vibrations. Okay. So, essentially this standard deals with, you know, like what is the how can we quantify the vibrations that come about when human beings are using a vehicle or machinery or tools in general, right. So, essentially we are going to apply it for our what is a vehicle systems analysis, right. So, this is a whole body vibration with respect to human health and comfort. Okay. So, typically it is agreed upon that when we are looking at vibration levels between 0.5 hertz to 80 hertz, we are interested in this range for analyzing human health and comfort. Okay. We have to analyze in this particular frequency range to decide what is the impact of a vehicle's operation on human comfort. And when we are looking at a frequency range of 0.1 hertz to 0.5 hertz, we are considering and we will be evaluating what will be the impact on so called motion sickness, right. So, all of us understand what motion sickness is, but that is essentially falls in a low frequency range, right. So, we can see that there is a huge range of frequencies over which the analysis must be done. Okay. And one comment here, please note that in the above analysis we are dealing with the angular frequency omega. How do we convert to what to say unit frequency in hertz? We have to divide by 2 pi. Okay. So, this is something which I wanted to point out, because sometimes like we should not forget to do this conversion, right. So, yeah, because we typically talk in terms of hertz, right. So, when we talk of these frequencies. So, let me quickly list 3 parameters which are used to quantify this. The base parameter is the weighted root mean square acceleration level. So, what is the acceleration level felt by the driver or the occupant of a vehicle, right. So, this is the base parameter to evaluate comfort levels, right. So, this weighted RMS acceleration levels, it is given by this formula. So, over a time period of observation capital T, this is represented according to this form. Okay. So, where this AW is a weighted acceleration, typically what is called as frequency weighting is done to get this AW, and capital T indicates the duration of measurement. Okay. And in this regard, there is an important parameter which is called as crest factor. What is this crest factor? It is the modulus of the ratio of the maximum instantaneous AW to its RMS value, what we have calculated above. Okay. So, that is the definition of the crest factor, and by and large this base measure like the above base measure, by and large it's people have found out that is normally valid and sufficient till crest factors till up to 9. Okay. So, that is this first parameter. Okay. The second parameter is when where there are spikes in the acceleration levels, then this base factor has to be replaced with others. So, then we have what is called as a running RMS method, which is used when we have occasional shocks and transient vibration. So, what is this running RMS method, how is it evaluated quantitatively? So, we have a parameter which is called ARMS at a time t naught, okay, which is, let me write down the definition, then I will briefly explain what it is. So, we essentially evaluated using this formula. AW is once again the weighted acceleration, right, frequency weighted acceleration, but here the parameter tau is nothing but what is called as integration time for running averaging. So, what we do is that like we select an instant t naught, right, some instant t naught, and then we evaluate this measure in a small range t naught minus tau to t naught. So, that is why it is called as a running average. So, the time window keeps on shifting, right. So, this is the integration time for running averaging, and using this we define a parameter called maximum transient vibration value, okay, which is abbreviated as MTVV, which is defined as maximum of this ARMS T naught, okay, in the period of observation. That is the definition of MTVV. Okay. I will just introduce one last parameter and then we would conclude this discussion on suspensions. So, the last parameter is what is called as a vibration dose value. So, what is this vibration dose value? This vibration dose value, you know, like takes into account when there are peaks in the acceleration. Suppose let us say, you know, like my car is driven and then like I go into a pothole, there is going to be a spike in the acceleration levels, right. So, then this vibration dose value is going to be more sensitive, it is going to react to those sudden peaks, right. And the idea is to essentially use the fourth power of the weighted acceleration levels instead of the second power. So, that is the idea. If you compare it to the RMS acceleration, so we are using the fourth power instead of the second power. So, that like the peaks will be more dominant, right, in deciding this parameter. Okay. So, that is the definition of the vibration dose value. So, people use all these parameters to evaluate ride quality and ride comfort. Of course, we need to measure these acceleration levels. Okay. So, I will conclude my discussion on suspensions here. So, we have looked at broad overview of automotive suspensions, different classes, components, operation, and a brief analysis using this quarter curve model for ride analysis. Okay. So, thanks for your attention.